Good morning, everyone. My presentation will focus on the extended sample posterior p-value as a tool for gene species distribution model checking. First, I talk about the framework. Ecologists use gene species distribution models, JSDMs, to model biodiversity hierarchically. This modeling method makes it possible to share environmental information between species and take into account correlations between species in the same analysis. Bayesian JSDMs are types of Hierarchical Bayesian Models, HBMs. We will therefore focus on HBMs and which are more general. We call the model used to generate the data probabilistic model. The model used to analyze the data and estimate the parameter is statistical model. HBMs involve two levels of parameter statistics, of statistical parameters, hyperparameters and latent variables or hidden variables. We will use the term true statistical model if the likelihood are equal and if the prior density of the latent variables are equal, and if the prior density of the hyperparameters are equal or different. We will use the term forced statistical model if the likelihood are different and or the prior density of the latent variables are different. As with for any statistical modeling approach, we need to check the model to achieve greater confidence in the estimation and prediction of the statistical model. As tools to check the model, we consider the extended goodness of a p-value, which we will simply call extended p-value, EP-value, without a general formula one for EP values. So EP values are tools defined by a discrepancy function. We notice that EP values can use discrepancy function without Y in the arguments. So with EP values, we can do a targeted check of the assumption made on the latent variables. For example, taking a discrepancy function as the minimum function of argument psi, where we compare several minimum values of the replicated latent variable and several minimum values of the rad psi drawn from the density pi, conditional and observed data, where the natural choice of this density is the posterior distribution. What is the preferable EP values? Preference P1 or property P1. With a true statistical model, the preferable EP value is the EP value which has a uniform distribution, at least asymptotically, for any discrepancy function in the real values. Preference P2, which a false statistical model, the preferable EP value is the EP value which has a more concentrated distribution around 0 and or 1. And preference P3, the preferable EP value is also the EP value which is less numerically expansive. P3 is particularly important for JSDMs which are already numerically extensive to fit. What is the framework? What is the state of the art for this approach to check-in models? A natural choice would be the extended posterior predictive p-value, EPPP value. Does not satisfy, but EPP value does not satisfy P1. As an alternative for the EPP value, we propose the extended sample posterior p-value, ESPP value, which use a singular posterior set of parameters, unlike the EPPP value, which use several posterior sets of parameters. What were our results? We extend the proof providing Gaussian to anti-level and prove that the ESPP value satisfies P1. To compare EPPP and ESPP values for P2, so far only in numerical study. For P3, we calculated general computational cost of the EPPP value and the ESPP value, and we found that the ESPP value has much lower computational cost than the EPPP value. We consider two scenarios in our numerical study. For P1, we use scenario 1. Scenario 1, a true statistical model. For P2, we use scenario 2, a false statistical model. We chose this discrepancy function equal to the minimum function of the argument psi. So what did we find? For P1, with a true statistical model, ESPP value numerically follow a uniform distribution, unlike EPPP value. This is in agreement with our mathematical result for the ESPP value. For P2, with the false statistical model, the ESPP values were more concentrated around 0 than the EPPP values. In the other word, the ESPP values were better at detecting departure between the statistical and the true prior densities of the latent variable than the EPPP values in this example. For P3, the ESPP values were numerically less extensive than the EPPP values. This is also in agreement with our general computational cost calculated for ESPP and EPPP values. In this numerical study, we have so far written only a singular core code with no height performance computing. After we considered other examples of discrete discrepancy functions, we found that the extended sampled posterior p-value is generally preferable over the extended posterior predictive p-value as a tool for checking hierarchical Bayesian model, gene species distribution models in particular. We are looking for other example of hierarchical Bayesian models to verify our finding. Thank you for your attention.